I am one of the PhD students from Klaus Knote that Stuart mentioned this morning. I didn't think of Klaus as an entrepreneur before that, but I see what you mean. And I'm also very delighted to meet you here today because I know Klaus and Inge Knote very well, and I have met Jost Kalker several times when I was PhD student, and I knew that your families have always been good friends, so it's really a pleasure to finally meet you here today. But having said this, I can also say that Klaus and Jost could have quite some arguments on on the technical issues. They had both strong opinions on things, and they could have initiated discussions. I think, Stuart, you remember some of those as well. Celie asked me to continue before I go into some of our own research, trying to relate it to Jost Kalker's work. Celie asked me to expand a little bit on the life of Jost Kalker, and what I'm referring to is also taken from the editorial to the special issue on vehicle system dynamics that Celie Lee mentioned before, and that editorial was actually written by Ken Johnson and Klaus Knote together. And I had some conversation with Klaus before coming here. He gives regards to all of you. He cannot travel anymore, and if he would have known that you are here, so I'm sure that he would give special regards to you today. Jost Kalker was born in The Hague in 1933 to a Jewish family, and his father was killed in Auschwitz. And if you allow me this comment, I think it's very important these days to remember this dark part of European and especially German history. He studied physics and applied mathematics at Delft University, and he did his graduate work, we heard a little bit about it already, at Dutch Rail under the supervision of De Pater, which I think many of us here know. The title of the master thesis was "The Force Transmitted by Two Elastic Bodies." He met Ken Johnson the first time in 1956 during a visit in Cambridge together with De Pater. And as we already heard from Celie Lee, and as we probably all know anyhow, in 1967 he defended his PhD thesis on the rolling contact of two elastic bodies in the presence of dry friction. And this thesis, I think, established the mechanics of rolling contact under arbitrary combinations of lateral, longitudinal, creep, and spin. Since 1979, he was full professor, as you already mentioned a bit, at Delft University on a personal chair in applied mathematics. And the good thing was that in parallel to the theories that Jost Kalker developed in ORE question C9, some experimental work was performed. Laboratory experiments were performed, and they confirmed his theory. And probably, as Ken Johnson and Klaus Knote wrote here, probably that is also one of the reasons why his theory prevailed, because it was very early validated by laboratory experiments. And they also write, it prevailed even though most of the people do not really understand the full mathematical background. If I ask the question first, how many of you have read, at least in part, the book Three-Dimensional Bodies in Rolling Contact? How many of you have read parts of it now? And how many of you have understood the whole book? Who dares to? The first 3 chapters perhaps are okay, but when he starts with the variational principles, I can say at least I stopped understanding the details.
It's not a bestseller.
It's a good book, but it's tough stuff.
Still sold now and then for libraries.
But we all, of course, know and we all use Kalker coefficients, contact, and FASTSIM. Jost advised 6 PhD students through his time as professor, and the last one was you, Seely Lee. And on retirement, sadly, he was a victim of Parkinson's disease. So I heard that he attended your PhD defense then in a wheelchair in the end because he couldn't walk then. If you want to see more details, look in the special issue of Vehicle System Dynamics, the editorial, but also in the papers that are included in that issue. Okay, and now I will come to some work that we have done and many other research groups do very similar work. And what does Jost Kalker mean for this type of work, and where might be some limitations of the work? So let me talk you through a little bit on how we deal with prediction of wear and rolling contact fatigue in our research group. You have seen from the beginning we are 4 authors on that. We could have put even more authors on that. We have been working on this probably for 20 years, and a lot of people have worked on this issue in our group. I think I don't need to talk a lot about this here in this group, but you know that wheel and rail wear or rolling contact fatigue issues can be a severe issue for railway operation, can cost a lot of money in maintenance or replacement of wheels or rails and so on. So we all know that. So therefore, we tried to develop methodologies to not only with field tests, but also with help of simulation, try to predict first the wheel wear. That picture has been presented before, that's not new, and also, as said, other research groups are working on that, I know. But the basic idea is that you build up a good multi-body simulation model of the vehicle you are studying. You gather as much information as you can about operational conditions to build up good simulation cases. Then you do simulation and calculate where do I really have wear on the wheel, where do I have wear on the rails, and after a certain time, if you do a wheel wear calculation, you update the profile of the wheel, and then you start the simulation again until you reach a certain running distance you want to reach. In this procedure, there are at least 2 issues which are important, and I will come back to them later. On one hand, you want to employ very good contact mechanics because you really want to know where do I have this sliding, where and how big stresses do I have in the contact. So you really want to know the details on the contact conditions. On the other hand, you have to do a lot of simulations, a number of operational cases, and then a lot of, as we call it, wear steps, so many simulations. So the contact mechanics you use need to be computationally efficient, otherwise it takes too long time to do these calculations, and this is important to have in mind. We have done come up with a very similar procedure even for RCF calculation. It's mainly the work of Said Hosseinia, who is here also. It's a lot of your PhD work, where we, again, do simulations, calculate the wheel-rail contact response, and then we do wear and RCF calculation. I will explain a little bit more about it. We do, on one hand, the RCF calculation, where we count, so to say, the exceedances of the yield limit, but in parallel, we also do the classical wear simulation to always calculate with the correct profile geometry, because this determines very much the stresses you have. If you have wrong profile combinations, then you get wrong stresses, and then everything gets wrong. Therefore, we do both in parallel there. But the basic idea is the same here. As said, on the left-hand side, you have the classic wear calculation, where we also use the wear map that has been mentioned many times during that conference already, and we use Archer's wear law. I will come back to this later also. And then at every wheel turn, we calculate the sliding speeds and calculate the amount of wear you have per wheel turn. And to judge the RCF risk of the profile, we check the exceedances of shear stresses. So do they exceed the yield limit? And because if you only consider rolling contact fatigue, crack initiation, crack growth, then you would overestimate the rolling contact fatigue risk. Therefore, we scale it by considering the wear, and there we use the wear law of Burstow. We just say if you have a large RCF risk but low wear on that part of the profile, we keep the high value of RCF risk. But if you at the same time have very high wear, we reduce or even remove the RCF risk. And this is shown a little bit on the right-hand side. On both parts of the profile, you might have more or less the same RCF risk, but on one part of the profile, you have very little wear, and on the other part of the profile, you have a lot of wear at the same time. I come back to this, not because I think you don't know it, but because I need it for later talk about Kalker's theories and what we use in addition to that today. As we have heard yesterday already, many of us use the Arcad wear law, where the wear is basically proportional to the sliding distance in the contact. You can translate it even to a local law where the wear depth, then it's a volume, there it's just the wear depth, is proportional to the sliding distance. And to know exactly where on the profile this happens, you have to divide the contact area into a mesh, say perhaps 40 elements or whatever, and then in each element you calculate the wear. If there's slip, then you get wear. If there's no slip in the adhesion zone, there's no wear. But here you can start to think, all of us have used basically the Hertz theory for the vertical contact and FASTSIM for the lateral contact. That means most of us have used elliptical contacts. But if you see this figure here, it's a little bit doubtful if elliptical contact is a good approximation. Here, in some contact situations, like here, for example, on the upper half, you always see the Hertz solution, and on the lower half, you see a more exact non-Hertzian solution. Here, it's not very much difference between the Hertzian and the non-Hertzian solution, but here is quite a difference between those two. And with a non-Hertzian solution, you might get wear here, but with a Hertzian solution, you don't even have contact there, so you can never get wear there. So it's worthwhile to think a little bit of this. And there also, if you use FASTSIM, there are also some limitations. You have to have in mind that before starting to do wear or RCF calculations, we were mainly interested in the total force from the contact, the integration over the contact stresses to calculate ride comfort, to calculate stability, curving behavior of a vehicle. And then I think even though there are some errors, this is fine. But if you want to really calculate stresses, then you have to think a little bit more. And then there are some limitations with FASTSIM. It uses a parabolic traction bound, which gives quite a good estimation of the forces, but a less good estimation of the stresses. A colleague of mine, Martin Sichani, that was mainly his PhD thesis, saw that the shear stress estimation error with respect to contact may rise to 33% at the point of contact. He also looked at strip theory that is used by a lot of people, which is quite good, but which also has some limitations. If you have a contact ellipse where A over B is larger than 1, then the strip theory doesn't work so well. And also for high spin cases, strip theory does not work very well. So Martin came up with a theory that tried to combine the strength of both FASTSIM and strip theory. For example, he used an elliptic traction bound and nonlinear growth of shear stresses from the stick zone to the slip zone, but it still uses FASTSIM to determine the direction of the stresses. Here you can see comparison between contact and FASTSIM. We can mainly look at the errors. They can go up to a little bit above 10% here for the lateral force. For the longitudinal force, it's about 10%. The maximum error you get when you use FASTSIM compared to contact. Above the same pictures, but below the pictures with FASTRIP, the new developed tangential contact theory, and with that, Martin could reduce the errors to being below 2% between contact and FASTRIP. Martin also looked at the normal contact, and I was very happy yesterday. I heard a colleague talk about Martin's solution, aniline, for example. That is what he employed in the vertical direction. And just the basic idea is that sometimes in the surface deformation is just neglected, and Martin's idea is to approximate the surface deformation instead of neglecting it. And then he uses, not as the Hertz solution, constant curve radii, but the curve radii can vary, and so he comes up with non-linear, non-elliptic contact patches compared to the Hertz solution. And using both aniline and FASTRIP, you can see on the left-hand side, you have the solution that you would get if you use Hertz and FASTSIM. This is contact, which we for now say that is the exact solution. And in between here, you have the solution with aniline and FASTRIP, which is actually relatively near to the contact solution. And when it now comes to the shear stresses, very important for rolling contact fatigue prediction, you can see that in the center of the contact with Hertz and FASTSIM, you get that shear stress distribution, and with aniline and FASTRIP, you almost get the same distribution as you get with contact. And if you look at a cross-section here, then we have the case which I mentioned before. With the Hertz solution, you don't even have contact there, so the shear stress distribution there is 0 with the Hertz solution, but with contact, you have a contact there, and you get a shear stress in that part of the wheel or the rail. So here we are at the trade-off again, which I mentioned before. You would like to employ the contact code when you do the wear or RCF calculations, but as said, since you have to do so many calculations and so many wear steps, that don't look too much at exactly the simulation times. They depend on so many things, but I can say even using Hertz and FASTSIM, it can take between 24 and 48 hours to do this, where prediction calculation, if you want to calculate up to, say, 200 or 400,000 kilometers. So actually, we are even concerned using Martin's theories, because if you have a factor of 10 and it takes 24 hours now, yeah, you can easily calculate, and even that is a step which is difficult to take. So it's really important to be numerically efficient, even with today's computer capacities. Here I want to show a result from Syed's work where he calculated the RCF risk, that means the number of exceedances of the yield limit, both with FASTSIM and with FASTRIP on a wheel. And here you can see the plot for the difference between the solutions. On most parts of the wheel profile, the difference is actually not that high, but here around the center point, the difference goes up to, say, 8, perhaps 8%. That was just one example. That was, by the way, I see I forgot to write, this is for the iron ore locomotives we have in Sweden, this example. Just shortly showing what type of studies can you make with this. Here we calculated the RCF risk for a number of different operational conditions on the iron ore line. For example, they use a lot of electrodynamic braking, and how does that influence the RCF risk? They experimented also with different wheel materials, so we calculated with another wheel material. They are even thinking of increasing the axle load further they have, so we calculated with increased axle load and also with different track gauges, because they have usually quite a lot of gauge widening there on their tracks. And how does that influence? So just to give you an impression, what type of studies did we do with this type of simulation tool? I want to finish with contradicting myself a little bit, also contradicting with what I said yesterday, that we work on a new wear model that is based on physics and not so much on empirical values. We did a lot of studies, wear studies, also using Hertz and FASTSIM, and actually in many cases we got quite good agreement between measurements and simulations. This is an example for the iron ore traffic in northern Sweden, this time for the iron ore wagons. And as you can see, after 150,000 kilometers, we got quite a good agreement between the measured, the starting or the measured and the simulated wheel profile. Another study we did was for Chinese high-speed trains. There we calculated, as you see, up to 400,000 kilometers. And you see after 200,000 kilometers, there were some deviations between the simulated and the measured profiles. But after 400,000 kilometers, we got an almost perfect match actually between simulated and measured wheel profiles. And the good thing here is we did not have access to the measured wheel profiles before all simulations were done. So we had no chance to adapt anything to the measurements that was done and even given out, and then we got the measurement results. I can say I was a little nervous, I have to admit that, but we got a good result there. So, to my last slide, what could we conclude from this? Even though Jost Kalker's FASTSIM algorithm has some limitations and using elliptic contact doesn't seem to be very obvious, in many cases you still get good results. And I wanted to give that picture because I remember I was myself so astonished as a student, Klaus Knote teaching me rail vehicle dynamics and contact mechanics, and when I saw what a rough simplification FASTSIM actually is, employing an elastic bed and a brush model where the deformation and the stresses the stresses only depend on the deformation at that point and not as it is in reality a load somewhere here also influences the deformation, or the deformation here influences the stresses everywhere in the material. When you just see this, you cannot imagine that you can get so good results with this, as it seems quite rough simplification. So, with that, thank you again, Celie Lee, for asking me, and thank you very much.